We've now got a strategy for solving matrix equations. To solve the matrix equation AX equals B, what we can do is start by forming the augmented matrix, then do row operations until the augmented matrix reaches some kind of nice form, and then from that nice form, step 3, we can read off the solutions. We now know a lot about this process. We know what we're going to use as a definition of nice form, which is row-reduced echelon form, and we also know that when we do row operations, we are not changing the set of solutions to our matrix equations, so this procedure actually will end up with us being able to read off the set of solutions to our original set of equations. The problem that we've got is that we don't know how to put a matrix into a row-reduced echelon form, and we don't know how to read off the solutions. That's what we're going to think about in this video. Here's 2 facts about row-reduced echelon form. The first fact, which I think is actually quite intuitive, is that every matrix can be put into row-reduced echelon form by doing row operations. What I mean by that is that if you have any matrix at all, then you can do a sequence of row operations to that matrix which finish up with a matrix which is in row-reduced echelon form. That becomes more convincing the more examples you do, and we're going to do an example on the next page. The next fact is not obvious at all. We don't actually need it, so I'm not going to give a proof of it, but it's useful to know that this fact is true. And what it is that if B and C are matrices in row-reduced echelon form, which result from doing row operations to a matrix A, then actually they're the same. So there is one and only one matrix in row-reduced echelon form which can be reached by doing row operations to the matrix A. That's why you'll hear people talk about the row-reduced echelon form of a matrix A. What they mean when they say that is that there is one and only one row-reduced echelon form matrix which you can get to by doing row operations to the matrix A. If you'd like to see a proof of fact 2, you can find a link to that in the online notes for this section. You can also find a proof of fact 1 link there as well. That's much easier. We're now going to do an example of putting a matrix in row-reduced echelon form. What that means is starting with a matrix which is not in row-reduced echelon form and doing a sequence of row operations until we reach a matrix which is in row-reduced echelon form. The matrix we'll think about is this one, the 3x3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is very much not in row-reduced echelon form. One of the reasons that it's not in row-reduced echelon form is if you look at the leading entry in row 1, that's a 1, so that's okay, but the other entries in that column are not 0. And in a row-reduced echelon form matrix, every entry in the column of a leading entry is equal to 0. So if we're to put this matrix into row-reduced echelon form, a good way to get started would be to use row operations to eliminate the non-zero entries in the column of the leading entry in row 1. That's easy to do because we have row operations which subtract a multiple of one row from another. So if we subtracted 4 times the first row from the second, then what we do is eliminate this 4 here. We turn that into 0, and that would help us get closer to row-reduced echelon form. So that's our first row operation. Subtract 4 times row 1 from row 2. When you do that, this thing here is the matrix you get. You end up with. You can see that rows 1 and 3 haven't changed, and row 2 now has a 0 in column 1. Repeating this for the third row, we want to eliminate the 7 here because we need all of the entries in the column of this leading entry 1 to be 0. So we subtract 7 times row 1 from row 3. That's this row operation here. Again, rows 1 and 2 are unchanged, but row 3 becomes this, and in particular, row 3 now has a 0. So when we're at this stage here, we do not have a matrix in row-reduced echelon form, but we do satisfy part of the definition of row-reduced echelon form, which is that there is a leading entry in row 1, column 1, and every other entry in the column of that leading entry is 0. So why are we not in row-reduced echelon form? Well, one reason is that there is a leading entry in row 2, just here, and that leading entry is not 1. In a row-reduced echelon form matrix, every leading entry must be 1. So a good step would be to make that leading entry 1 by multiplying row 2 by an appropriate constant. So if we multiply row 2 by minus a third, then the leading entry in row 2 will be 1. That's what this next row operation does. It multiplies row 2 by minus 1/3. You can see here that rows 1 and 3 haven't changed, but that row 2 now has its leading entry equal to 1, so we're a step closer to row-reduced echelon form. We're still not in row-reduced echelon form, however, because we have a leading entry in row 2, and we have other non-zero entries in the column of that leading entry. That we have the 2 here, and we have the minus 6 here, and those things are stopping us from being in row-reduced echelon form. So what we're going to do is subtract multiples of row 2 from the other 2 rows in order that we satisfy the row-reduced echelon form condition that the other entries in the column of a leading entry must be 0. So to eliminate the 2 in row 1, we'll subtract 2 times row 2 from row 1. When we do that, we get to this matrix here. You can see that rows 2 and 3 haven't changed, but row 1 has changed, and now it has a 0 in the column of the leading entry in row 2. We still have this problem that there is another non-zero entry in the column of that leading entry, namely this one. And to eliminate that, what we need to do is add 6 times row 2 to row 3. So that's the next row operation to do. On doing that, what you'll find is, again, rows 1 and 2 haven't changed, but this time row 3 actually has become 0, 0, 0. And if you now look carefully at this matrix, it is in row-reduced echelon form. It meets all 4 conditions. It has a row of zeros, but that row of zeros is at the bottom. All of the leading entries are 1, so there are the leading entries. The entries in the column of each leading entry are all 0, so you can see that that's true looking at those first 2 columns. And finally, the leading entry in row 2 is strictly to the right of the leading entry in row 1. All 4 conditions have been met, so we have found a matrix which is in row-reduced echelon form. Let's now look at how we might solve a linear system whose augmented matrix is in row-reduced echelon form. This is an example of an augmented matrix in row-reduced echelon form. We're going to translate that back into a system of equations. So if the variables in this system were named x, y, z, and w, then the equations would say that, first of all, from row 1, x plus 2z is equal to 0. So remember, the last column is the matrix of the vector of constants. So the first equation would say x plus 2z is equal to 0. The next equation from row 2 would say that y plus 4z was equal to 0. So that's row 2. Looking at row 3, this equation would say that w is equal to 0. And finally, looking at row 4 says 0 times x plus 0 times y plus 0 times z plus 0 times w is equal to 1. That's a problem because it says 0 equals 1. Well, it's not a problem. I mean, what it's telling us is that the system of linear equations has no solutions. The last equation is impossible, so there are no solutions to this linear system. Let's take now the same system of linear equations, or rather the same augmented matrix, except with a slightly different final column. So I've kept the first part of the augmented matrix the same, but I've changed this last column. Now if we read off the equations with the same variable names as before, x, y, z, and w, the equations we get are, from the first row, x plus 2z is equal to 2. From the second row, y plus 4z is equal to 3. From the third row, w is equal to 4. And this time the final row was all zeros. So what the final row would tell us would be simply 0 equals 0. In fact, we can ignore this last equation. It doesn't give us any information at all because it's simply something which is always true. So we have a system of linear equations from which it's now easy to read off what the solutions are. It's clear that you can choose the value of the variable z freely, and once you've chosen that value of z freely, you then are in a situation where all of the other three variables are uniquely determined. Once you've chosen z, then you know that x is equal to 2 minus 2z, y is equal to 3 minus 4z, and w is equal to 4, just rearranging these three equations here. Sometimes when we've read off these solutions, we write them in a vector form. For example, you might write x, y, z, w is equal to z times minus 2 minus 4 1 0 plus 2 3 0 4. This form is called the vector form of this solution, but it expresses just the exact same thing that I wrote down at the bottom there. So you can see that the fact that this matrix was in row-reduced echelon form made it really easy for us to actually see what the solutions to the system of linear equations were. In particular, we were able to see that the variable z could be chosen freely, and that then every other variable, x, y, and w, was uniquely determined in terms of that variable z. Here's a summary of how to read off the set of solutions to a linear system which has an augmented matrix in row-reduced echelon form. The first step is to look at the last column. If the last column has of the augmented matrix has a leading entry, there are no solutions at all to the linear system. That's because if the last column has a leading entry, then there is an equation in your linear system of the form 0 equals 1. There can be no solutions to such an equation, and therefore there are no solutions to your linear system. Otherwise, variables corresponding to a column with no leading entry, like z in the example we've just done, can be chosen freely. Those variables are called free parameters because they can be chosen freely. And it then follows that all the other variables are uniquely determined in terms of those free parameters. And that's it. That's how we read off the solutions to a linear system whose augmented matrix is in row-reduced echelon form. We can now solve any system of linear equations by finding the augmented matrix, doing row operations until the augmented matrix is in row-reduced echelon form, following the procedure on this slide to determine the solutions, and then we know that the solutions that we've got are precisely the solutions to the original system of linear equations.